I'm delighted to be here in Australia again, in Melbourne again. I only know Melbourne in Australia, but I've been here many times. And I'm going to echo what our president from the IGS mentioned, but I'm going to clarify one thing, that is that if you're a member of ACIGS, ACIGS or ACIGS? ACIGS? ACIGS. You're automatically a member of the international AGS. So all the benefits that Chung-Sik mentioned that you may have as a member of the International Geosynthetic Society, you automatically get them once you're a member of ACIGS, which is different than in many other societies where you need to be separate members for the Geotechnical and the International Geotechnical Society, for example. All right, we're going to be talking about today about transportation, and my first talk is going to be at the heart of there is an important growth in the use of geosynthetics for roadway applications. So within the family of applications that we have for transportation applications, we have the subfamily for roadway applications, and I'm going to go even deeper. I'm going to go into their use for the case of roadways over expansive clays. I'm coming from Texas. And in Texas and in Australia, this is the culprit. The culprit is that we do have some clays, by the way, they are the smallest clays, particles, that will have are so tiny that their behavior is dominated not by the gravitational forces, but by the electrical forces. So here as a reference, you see a particle of quartz, and this is smectite. What is smectite? Smectite is one of the many silicates that form our soils. All our soils, for the great majority, they are silicates. And they are in its most unit form. The unit cell is what we call a 2-to-1 unit. It does have a tetrahedral silicate, and it has an octahedral unit sandwiched in between. Each one of these together could form a clay particle. Why I'm telling you all this? It turns out that these are not just particles. There is an effect that is called isomorphous substitution, by which that is called isomorphous substitution, in which some atoms, in this case magnesium that has a valence 2, kicks out atoms of valence 3, aluminum, and suddenly our clay becomes negatively charged. What this does is that in order to satisfy the electronegativity of the clay, cations need to come to the rescue and satisfy electrically the system needs to be electrically neutral. But when the cations come, they also come with water. And when water comes, these two particles change distance. And when there is no availability of water, the cation is still there, but the thickness of the distance between consecutive clay particles decreases. This creates what we call shrink swell soils, or expansive clays, or expansive soils. And this creates a significant problem. A significant problem because essentially if we have unhydrated, in this case it's bentonite, then we add water, it will swell. And if we have pure clay, pure smectite, pure non-marginalized, we're talking about 200, 300% volumetric changes. So 3 times the volume. That's humongous. What we're going to see then is that in the US, we do have a significant fraction of our soils have expansive clays. Here in all central US, everything that is blue is, that's not good. We have a significant fraction of expansive clays. Everything that is red, just get out of here. Don't you think come here. Now, but there is a problem. There is a problem because I'm coming from Texas, and this is a blowout of Texas. And here red, for example, this is the Eagle Ford Formation. And along the Eagle Ford Formation, if you're familiar with the US, that's Highway 35. We do have Dallas, Fort Worth here. Here we have Austin. Here we have San Antonio. So 3 or 4 of the 5 most important cities in Texas are exactly where we should have never considered building our cities. But Australia is not that much better. So as doing some research, I realized that much of your territory, in this case it's blue, should have been dark red, you do have a significant abundance of expansive clays. So all the problems that I'm going to tell you about Texas, you have them as well. And the detrimental effects of expansive soils are such that we're going to have problems in foundations. But the real most important problems are going to be in lightweight structures, because when we have heavy structures, the weight compensates for the tendency of the clay to swell. The real problem is going to be in lightweight structures, in houses, not in buildings. In houses, you're going to have a problem, or in roadways. Roadways, we're going to have significant problems associated with the presence of expansive clays. And essentially what happens, particularly if you have a reasonably low volume road, then water is going to cause soil to swell during the wet season, and it's going to cause the soil to settle and shrink during the dry season. Now, in a roadway, the access to water typically comes from the shoulders. So during the wet season, we're going to have that the shoulders are going to heave, and during the dry season, the shoulders are going to settle and heave and settle. And they are going to do this quite often. And during when you are in potentially a significant dry season, and this is a flexion. It has nothing to do with traffic. During the dry season, suddenly you're going to see the fingerprint of the problems that happen with expansive clays that are going to be longitudinal cracks. These longitudinal cracks have nothing to do with traffic. Sometimes we do have these longitudinal cracks soon after opening it to traffic. The problem is changes in moisture. Now, and this is nearby my house, not my home. This is nearby Austin, Texas. You see these humongous longitudinal cracks that are essentially caused by the presence of expansive clays. These are the Badlands. These are San Antonio, Texas, Bastrop, near Austin, Texas, and thank you, Rod. So Adelaide, in South Australia. So you may start looking at your roadways, and if you see crocodile type of fatigue, that's fatigue. If you see longitudinal cracks, you're in expansive clays. That's not caused by traffic loads. All right, so in Texas, we make a significant investment in order to mitigate the problems associated with expansive clays. There are different criteria. Designing roads is much more difficult than designing walls or roads. We design for serviceability. And that makes our design significantly more complex than what we typically do if we care about collapse, that's easy. If we care about deformations, that's difficult. In Texas, we have a criterion that is called PVR, potential vertical rise. It's an index. Essentially, it tells us if you have a profile of soil, different types of soil, and suddenly this profile becomes saturated, goes from reasonably dry to saturated, then the ground is going to heave. May never happen, but we predict what would happen, what would be the heave if that happens. And we're talking about 3 inches, 10 centimeters. 10 centimeters, 5 centimeters, 2 centimeters. So the criterion for design is that at no point you need to have a heave of more than 1.5 inches. So that's on the order of 4 centimeters, which is a lot. But this is, think of Melbourne getting inundated. or algae becoming inundated. At that point, you cannot have more than 4 centimeters of rise, which is a lot. But very often you will have much more than that, 10 centimeters, 15 centimeters, and that's an index. And depending on what your index is, you do have different remedial situations. Yes, please.
Are those measurements free swell, so no loading in the assessment?
Okay. No loading, that's a very good point, and that takes me to my next slide, which is something that I'm not going to tell you about. I'm just going to give you a taste. I'm a geotechnical engineer, so in addition to geosynthetics, I work with flow of soils under unsaturated conditions. So they do a free swell. One way to characterize the swelling is doing a free swell. The problem is that, at least in Texas, no one did it. No one does it. And it's not because it's difficult, it's because it takes a long time. It takes a month or two to get one data point. And you need to get your data points not on the free swell, but at different confinement. Because what you want is the swell stress curve. One thing that we did at the University of Texas, and it has been implemented by TxDOT very, very recently, is let's do the swell test, but in a centrifuge. So essentially, not only we add the load, but we also increase the gravitational forces, we increase the gradient, we increase the potential energy. And suddenly, we can characterize, essentially the water moves faster, and we can get what we typically would get in a month or so. We are getting multiple data points in a day or so. So here we have the same clay. In red is when we reached the swelling using a centrifuge technique, and here we have in blue, essentially, and here this is a log scale, here we're in 20 days and we still have a way to go, using conventional free swell techniques. The problem is that no one is going to wait for 20 days or 30 days, so essentially we rely on correlations that were run 50 years ago, and those correlations are correlations with Zornberg limits. So we have a few data points where they run some correlations, they make the multiple corrections, and based on that they make, in Texas, until very recently, they would make multi-million-dollar decisions on whether you have a problem, and if you have a problem, what solutions to make. But I'm just going to give you a taste of this. Just let's say that we do have a problem. You realize either because of past history that the road we have these longitudinal cracks and we know that we have a problem, or you characterize the soil in a certain way and yes, you do have a problem. So now let's come up with a solution. And that's what I'm going to focus the most. Just for those of you that are not transportation engineers or even geotechnical engineers, let me give you a ADC on roadways. So essentially we have a multi-layer system, and what we're going to ask from this multi-layer system is just be stiff. We want stiffness. Why we want stiffness? Because if we have a truck, the truck load, several tons, 10 tons, those 10 tons will make it to the subgrade. No way, that's statics. We cannot avoid that. What we want is that those 10 tons make it to the subgrade in as wide of an area as possible. We want the pressure contact to be as small as possible. Even though the load, we cannot decrease it. So because of that, we're going to have typically an asphaltic surface. I'm going to be talking about what we call flexible pavements with asphalt, which are the great majority of them. Then we have a base, which is a very, very expensive material, granular, free-draining material. Sometimes in Texas, well, always in Texas, but sometimes in the rest of the world. Do you have sub-bases in here? Yeah. Okay. You may have somewhere in between. You don't spend so much money on this high-quality gravel. Just let's get something better. And then you have the subgrade, whatever you have. In this case, we're going to focus on expansive clays. All right, and we're going to talk about how do we make use of geosynthetics. Surprise, to solve this problem. There are several ways, but one of them, and the one that I'm going to focus on, is on the use of geosynthetics to solve this problem. There are several types of geosynthetics that can be used, including geogrids, geotextiles, geocells. Now, it turns out that when you have a geosynthetic, you have a number of functions that you need to address. there's a big debate in the geosynthetic industry on how do we call, terminology is very, very important, so we need to understand each other. So I'm going to be very careful. If you have not been part of this discussion, I'm going to tell you that what I'm going to show you, not everyone agrees. But let me tell you what are the different functions with the terminology. What are the different functions that we can ask for geosynthetics to come to the rescue on our roadways? And we can ask several hydraulic, mechanical functions. We can have separation to essentially maintain the subgrade. Okay, maybe bad, but okay, we're going to keep it. But if the subgrade contaminates my base or my subbase, I really have a problem. So let's keep things separate. Then we have reinforcement. It's a mechanical benefit. It's developing tensile loads, but what I want to avoid is failure. What I need the most in here is high tensile strength. Then, and this is new, I have another mechanical benefit, function, which is I want tensile forces, but I want the tensile forces to control deformations. And I'm going to call that stiffening. It's mechanical. Some would call it also reinforcement. I'm going to call it stiffening because I really don't care about the tensile strength. If this road, in many cases, reaches tensile strength, the road is by far gone. So I really want to control deflections. And in addition to that, I may have hydraulic functions, filtration, and barriers, and drainage, lateral drainage. So here we have an entire portfolio of functions that can come to your rescue when you have problems in your roads. Or even if you don't have problems, if you want to make your design more cost effective or extend your design life. All right, in this presentation, I'm going to be referring only to one application and only to one function. And that application and that function is going to be stiffening. And I'm more specifically going to focus on the stiffening of the base here. Everything that I showed you in the previous slide, another day we can talk. Today, I'm only going to be talking about stiffening and stiffening of the base. And this is very often what we call as an application that is base stabilization. Again, so why are we going to care? We can use this base stabilization against traffic loads, but in this case, I'm going to focus on environmental loads. Sometimes we call it environmental loads. So it's essentially when this roadway flexes, develops those longitudinal cracks. Sometimes actually during the wet season, those cracks close a little bit, maybe 3-5 millimeters thick, wide, and then they close to 1 millimeter or even less. But the damage is already there. Once you generate the crack, water is going to get in, and that initiates a process of degradation of the roadway that would have not been there without the longitudinal crack. So again, I showed you this picture, but we went and we measured this mechanism, and really the roads, the shoulders go up and down, as I've just showed you. And there was a lot of discussion whether this is the actual mechanism that occurs when we have an expansive clays. Now, it turns out that in Texas, for the last 10, 20 years, they have realized in a reactive way, they tried things. And they tried it because not only we have expansive clays, a typical solution would be let's use lime stabilization to kill that swell behavior of the clays. There is a problem in Texas. I'm not sure if you have the problem as well here. Is that if you have lime, you create a basic environment, but if you have sulfates, and that's common in Texas, then you create a mineral that is creates more volume changes than the swelling clay. That's ettringite. So if you have expansive clays and sulfates, you are doomed. So you really have a problem. And because Texas did have very often that problem, they said, let's try things. And they tried geosynthetics in the base. And it worked. So here we have FM19. FM means farm to market road, low volume road. 1915. Here we have a section without longitudinal cracks. Because they had put, there are expansive clays, but they had put a geogrid in this particular case on the base material. But they left the control section, no longitudinal cracks. A lot of longitudinal cracks. And then let's add the geosynthetic, but let's even reduce by 30% the thickness of the base. And guess what? No longitudinal cracks and cost savings, because you did decrease the required thickness of your base. So lesson learned. So geosynthetics reinforcement prevented the development of longitudinal cracks. However, so we didn't know, we know that it works, but we did not know why. And then we need to put our finger in what is the property, how do we specify, why did it work, are all geosynthetics going to be the same, then give me the cheapest one and it should work. That's not how it works, because here they didn't know exactly how to specify it. At the time they did use the tensile strength, which it should not use. Product A that meet the specs from Texas at the time, no longitudinal cracks. Product B, same met the specs, longitudinal cracks. More than that, all junctions have failed. So lesson 2, the current at the time, geogrid specifications have not led to consistent behavior. We knew that it worked, but we didn't know why, and we didn't know how to differentiate those that work from those that do not work. Big problem. We were working on this. We told them, yeah, put this because it's going to work. And suddenly I got a call. Texas. And we have just placed it. We didn't even open to traffic. And we have a longitudinal crack. Come and see it. Okay, here it is. Yes, longitudinal crack. Let's do a forensic evaluation. Let's dig a trench. No geogrid. Actually, the geogrid did its work. And the longitudinal crack did appear, but exactly where the geogrid did end. So the problem was that the contractor had used a 2 meters less wide rolls than what it should have. So essentially, the geogrid, it was a very expensive research exercise, but the geogrid did what it had to do, which is to eliminate the presence of longitudinal cracks, but certainly one condition. If you want your geogrid to work, then it needs to exist. Okay, so we know that it works. We do not know how it works. We do not know how to specify it. We did a major field project. These are one of those very time-consuming, expensive, long, ungrateful field experiences. We have 32 test sections. 3 different geosynthetic types, control sections, and lime and no lime stabilization. Texas, the use of lime is not to treat the subgrade. They may treat the subgrade as well, but the most common type of use of lime is they treat the subbase. Do they do that here? Subbase? Okay, don't do it. Don't keep doing it. I'm going to show you. So this was a low volume roll that was reconstructed. This is before reconstruction. And here are the different sections after reconstruction. So here we have control sections, control but with lime stabilization of the subbase, geosynthetic only, and geosynthetic and lime stabilization. All right, I'm not going to tell you the entire story, but this is, just wait until the dry season comes. It turns out that a particular year, 2011, was a record-setting dry season. So, no surprise, before we were doing condition surveys. And we were very specific. We were not focusing in all the measures of degradation of the roadway. We were only focusing on the degradation that occurs because of expansive place, which is the length of the longitudinal cracks. All right, so yes, we expected cracking, and we did have it. So visually, before putting numbers, this is a view of two lanes. The lane to the right is the control section. The lane to the left is a stabilized section. There's no ambiguity on the fact that the geosynthetic stabilized the base, and in the process of doing so, it did minimize the development of longitudinal cracks. These are the real numbers. We have 32 cross sections, 8 different types, 3 repeats for each one of them, and this is after averaging things. This is the take home. Control. We measure the percentage of longitudinal cracks. That is, let's get all the longitudinal cracks that are wider than 3 millimeters, and let's measure the entire length. Could be more than 100%. So if you have several longitudinal cracks that are parallel, you may have more than 100% longitudinal cracks. The control sections, 66% before and after, over the period of 1 year. 65% development of longitudinal cracks. Lime stabilization, not any better. Not any better, and I can tell you why. My worst enemy today is the lime association. And to be fair to them, the problem is not, if you were gonna kill these volumetric changes because you're gonna treat the subgrade and you're gonna replace and treat 0.5 meter or 1 meter of subgrade, good luck with your budget, but that can do it. But in Texas, what they do is they stabilize the subbase. They rigidize the subbase. So it's going to be good for rotting, depth. But guess what? Now the volumetric changes continue, but now you have a brittle layer. You have created a brittle layer. So those volumetric changes that continue to occur now trigger the crack. We want to avoid the triggering of the crack. Trigger the crack more easy. And if you are going to do it, if you're going to use lime stabilization, then you need to go all the way. You need to kill the volumetric changes, and that's going to cost you. If you go halfway through, go geosynthetics only. And 3 different types of geosynthetics, all of them, no surprise, all of them, it's not that no longitudinal cracks, and not all geosynthetics are equal. This is what today we call type 1 geosynthetics, the lower tier of the geosynthetics, but the difference between performance with and without geosynthetics is striking. And in this particular case, and again, it's not surprising, I'm going to show you why, the 3 geosynthetics performed reasonably equally. This is the real data. So this is the survey immediately before the dry season. This is the survey after the dry season. Here we have the 3 different geosynthetic stabilized bases. This is the control. Significant difference in performance. And this is the lime stabilized. Definitely not performing well. All right, so we need to solve this problem. We know that it works, but we need to specify it, and even better, we need to design for it. So what makes this work? So back to the basics. We're talking about stiffening. And I showed you that slide, but what I didn't show you is the mechanism that had been discussed in the literature for quite some time on why these geosynthetics do work. There have been 3 theories. Theory number 1, membrane support. The concept being that if you have your geosynthetic and you have rotting depth taking place, then there will be a component on the tension that is vertical. And that vertical component helps in minimizing the load of the traffic. However, the level of rutting that you need in order to start mobilizing that vertical component is so humongous that for all practical purposes, in paved roads, in unpaved roads it is a different story, but in paved roads, this mechanism, if it exists, is negligible. There is another mechanism that has been considered, which is an increase in bearing capacity. So if we have a bearing capacity problem, traffic load that generates shear surfaces, potential shear surfaces, and you put a geosynthetic and you change the location of that shear surface, by doing so you bump up your factor of safety. But again, in this case, as in the previous one, the level of shear deformations that you need in order for this to be meaningful is so large that this is not working. This is not the relevant mechanism. There is consensus in the technical literature that the mechanism is lateral restraint. Let me ask you a question. Is a gravel, clean gravel, angular gravel, is a good material or a bad material as a foundation? Is a good gravel a good material or a bad material?
Good.
Good. Anyone says good? Who says good? That's good. Who says not good? You need to say either good or not good. You cannot not say anything. So,
how clean is the gravel?
Yeah. Depends what kind
How
of
clean is the
gravel.
gravel and what's the particle size distribution?
yeah, a gravel, choose your best particle soil distribution. You choose it, the best possible one. So, it's a good material.
Yes.
Yes. It's a bad material. Okay, I'm going to take that you agree that it's a good material. It may not be. A gravel is a good material only and only if confined. If you have a granular material that is unconfined, that's a very lousy material. You'd rather get your expansive clay. If confined, the gravel will be the best. So keep that in mind, because what happens? It turns out that with the traffic load, there is a tendency for that gravel to displace. There are permanent displacements within the gravel. And essentially there's a domino effect. When you place a gravel to begin with, it's compacted, highly compacted. Good confinement. But then if you have a little bit of lateral displacement, you do not need a lot, a fraction of a millimeter, then you lose confinement. If you lose confinement, you lose stiffness. And if you lose stiffness, you have a highly concentrated contact stresses, and you lost a lot of the benefit of your ground. So what the geosynthetic does is essentially restrains that lateral movement that ultimately will degrade the modulus of your base. And there is consensus in the technical literature that that's what happens. So what the
Obviously, you're talking about, I guess, country roads. What about in suburbia where you have a concrete curved channel where you have that confinement?
That it also happens. It's not going to be the case when you have a high volume road, because in that case you do have such a structural capacity that typically the main mechanisms are not necessarily losing the stiffness of the base. But we're not talking about that the entire road widens. It's essentially at the location of the wheel path is when you will have that lateral unconfinement, and that's exactly where you need it the most. But that's a very, very good point. So my answer to you would be yes, that's also the main mechanism. And the concept is that if you do have the geosynthetic developing tensile forces, many good things will happen. Essentially, we know that in the base we're going to have a reduced vertical stress, a reduced vertical strain. We're going to have a reduced straining. On the subgrade side of things, we will have a reduced vertical stress, which is always good, a reduced vertical strain, a reduced shear. So many good things will happen if we develop that tension and we keep the stiffness of the base.
If you move your grid to the center of the layer, will that provide you better confinement?
That grid goes the entire way.
Yeah, if you take it to the center.
To the center of the layer, absolutely. Absolutely. It's not only my research and many others say that what Malik is saying is, what about if you put it here? That's much better. But two problems. And why we don't do it. In Texas, there's only one district that does it. Two reasons not to do it. First, the contractor is going to hate you. So the idea is that, okay, do everything that you have done so far, prepare the subgrade, and before you start placing the base, just unroll my geosynthetic. That's it. No difference in construction. If you put it in the middle, then there's one more step. You need to place, let's say, half of the base, level it, place a geosynthetic, and continue. It's not a big deal, in my opinion.
No,
And the benefit is very significant. I did not manage to convince him yet. There's a second good reason, is that typically at this location is where you also need a separator. So some could argue that when you place your geosynthetic is doing the two functions, separation and stiffening. If you put it here, and we're talking about expansive planes, you would need a separator in any case. So we're talking about potentially a second geosynthetic as well, because you need it for a different reason, but you would need it in there.
You will need it anyway, because you have two different materials, so you need to separate them.
Correct. But some would argue that here one geosynthetic does both functions. So in some cases, what may be a bad thing is that if you say, okay, put it up in the middle, oh, by the way, you do not need it at the interface. You do need it in any case. So
Yeah, I think the design needs to be changed.
Yeah.
So obviously, you have two different functions.
no question about that. No question about that. And I fully agree, but I don't know. How do you do it in here in Australia? Do you
We
ever?
sandwich in between.
Hmm?
If it's a powering platform, you sandwich in between the platform.
In between? Okay. So you do better. And definitely I would endorse
We
that.
save a lot of money because maintenance work is pretty
Yeah.
much reduced.
So I would endorse that definitely. That's not the way that is done in the US, and the main reason is the contractors.
Surely you'd have to have a minimum cover over the top of it as well.
Mhm. Absolutely.
And then you have
Absolutely.
issues with your compaction we test with new makers.
Yeah. No argument. It's settled. I'm sold, but I was not able to sell this yet at home.
One way is to bring your DOT guys here. We can teach them.
That's a good idea. I'm sure that they would buy it. All right, but continue on this. Give me a property. All right, so we need a new property. The properties that we had so far didn't work. Why do we need a new property? Well, in the early days, everything that we knew about reinforcement was coming from everything that we knew about earth retention systems. So we knew how to design walls and slopes, and for that we design against collapse. We need tensile strength. However, now we're talking about a different animal. And until very recently, it hurts me, but all the specs that I've seen for using geosynthetics for this application specified tensile strength. Please don't do it. You don't need your tensile strength. What you need is a measure of your stiffness. And so we need in roadway systems, essentially, we don't care about collapse. If the geogrid or geosynthetic fails in tension, way before that, the road has failed because we care about serviceability. So the ultimate goal is to minimize distress. We need service conditions. So we need to characterize the development of tension under small displacements, essentially a stiffness. I'm not gonna. So how do we go back to what is the relevant property? Remember that I told you the different mechanisms, and we know that these either are not relevant at all, or certainly they are essentially negligible. So let's focus on this. It turns out many tests have been, many proposals have occurred trying to mimic that situation and come up with relevant performance tests. Most of them failed because of repeatability. Most of them were looking into the cyclic nature of the loading. I said, forget it. I don't care about the cyclic nature of the loading. Why? Well, because the cyclic nature of the load generates permanent deformations. And the permanent deformations are the ones that are going to load my grid. So the gravel doesn't go back and forth. The gravel displaces laterally, and then a little bit more, and then a little bit more, and loses confinement. So for all practical purposes, what I care, which is how my geosynthetic is loaded, this is a monotonic loading, but it's under the confinement, and is under low displacements. So the entire focus of this was essentially, let's try to reproduce this response. And it's confined, it's a sole geosynthetic interaction, but it's not cyclic. So, yeah, and again, this is a view, and even though I'm going to be talking about expansive clays, this which goes way beyond expansive clays. This goes increased structural capacity, increased longevity, the design life of your road, decrease the required thickness of your expensive base material. So the idea is that if you have a non-stabilized road base, with time, you're going to have those deflections, and with those deflections, this is exaggerated, but with those deflections, you lose confinement and you lose stiffness. The idea is that now your geosynthetic essentially will minimize or hopefully prevent those lateral displacements from taking place, and consequently the changes, the degradation of the modulus of your base. All right, so we're sold. I work with the Department of Transportation, and the idea was to define a single, however relevant parameter. By the way, this is what they told me. Don't you dare come up with a sophisticated model that requires 5 parameters. If you give me anything other than 1 parameter, it's never going to work, because I need to write specs. And if you give me a model that tells me, okay, this parabola or this line needs to be above a certain space, that's never going to cut it. Give me 1 number. So it had to be a single parameter, but relevant, that quantifies, that this is a mouthful, quantifies the confined stiffness of the solid geosynthetic composite under small displacement. It's confined, its stiffness, and if it is of the composite. So we went to the lab, and it turns out that in our geosynthetic business we have kind of a test. I'm not sure if you have it, Warren. So we do have a test, which is a pull-out test, that has kind of the setup, a little bit of what we need. We don't care about pull-out resistance, but before I get there, I'm not going to show you the math. but working out with some constitutive models, and the objective of the constitutive models was not necessarily to be accurate, but to solve a differential equation that governs this problem. And we solved it. And this differential equation, we had to make important assumptions. So we did not know if the assumptions were so brutal that our problem becomes decharacterized. So it turns out that if you do that test, this essentially tells me that the tension at any point within my geosynthetic squared is directly proportional to my displacement at that point, u. And the constant of proportionality is what we're looking for. And the constant of proportionality is what we call the stiffness of the solid geosynthetic composite, or KSGC. This comes from an analytical development that I'll be happy to give you with many simplifications. And essentially, it's telling me that if I run my test, or in the field, this is how this geosynthetic behaves. And if you do this analysis, it turns out that this is kind of neat, because it tells me that this confined stiffness is a product of two parameters. Is a product of the stiffness of the geosynthetic in itself times a measure of the interlocking, or of the interface shear transfer. So essentially it tells me I need both. For me to have this confined stiffness, if you give me a very, very stiff steel, but the interaction is not good enough, that's not going to cut it. If your interaction is very good, but it's not stiff enough, it's not going to cut it. For you to have this required stiffness, you need the good balance of both. Okay, let's go to the lab. So we know how to run this test. The main difference is that I'm going to have internal points within my geosynthetic. It's going to be under the confinement of soil. And I'm going to measure displacement as I load it. So actually, I'm not going to get into the details, but a very, very important piece of information is each one of these points, at the moment that displacement at that point is triggered for the first time, what is the frontal load? If I get those pieces of information, I can come up with the essentially unit tension and displacement at different points. Now, let's run a test. This is my setup, and this is the testing. We have tons of, based on our history of running pull-out tests, a lot of recommendations and ASTM standards and sizes. This is why this is huge. All right, so let's run a test, and this is my wish. So my wishful thinking is that after I run my test, and I plot, after I run my test, and I plot t squared versus u, I'm really going to cross my fingers. And I'm going to hope that at each LVDT, at each point of displacement, everything is going to go be linear. More than that, it's going to be linear and through the origin. But more than that, this is my wish. My wish is that, but here I have 1, 2, 3, 4, 5 points. That's point number 1. What about point number 2? It not only needs to be linear, but it needs to be the same line. So point number 2, and point number 3, and point number 4, and point number 5. That's my wish. It's not asking for little. I need all those, the property to be unique. Essentially what I'm saying is that if I get the property out of any point within my geogrid, I'm going to get the same result. It's a single, unique property. I'm not sure if it's going to work. So I'm going to run my test. This is frontal tension versus clamp displacement, which is a measure of same time. Frontal unit load versus clamp displacement. 5 displacement sensors versus frontal load. And now I can put it together. I measure displacements, frontal load, and clamp displacement. This is LVDT1. Unit tension versus displacement. Looks like a parabola. I'm getting excited. And let's square this. If I square it, I look at this and I say a line. Remember that we're talking about stiffness. Those of you that are used to measure resilient modulus, who here measures resilient modulus for rollers? Okay. If you get a scatter of 50%, you are ecstatic. That's excellent. We're talking about stiffness. We're not talking about strength. So, but that was my linear relationship, and the slope of that linear relationship is what I'm looking for. But I have 5 LDVDTs, 1, 2, 3, 4, 5. Different length, because the one at the very end just has a little bit of displacement. If I plot all of them are going to be aligned. All of them, the line is through the origin. All of them define the same, give or take, with some scatter, the same stiffness. The scatter that we're measuring, and our goal is to decrease it, is on the order of 20%. Okay, we went to TxDOT. We solved your problem. We can give you the answer. Here it is. Go and use it. No way. How long did it take for you to run one test? 3 or 4 days. It's never going to happen. Go back to the drawing board. And we did something that in the geosynthetics business could be a heresy, which is a small pull-up box. And we have books and dissertations and PhD degrees and papers telling you why you need that humongous box. But it turns out, so our box is small. Our box is small, and more than that, it's efficient in the sense that it fits in a wide width tensile load frame. So let's replace, this is a wide width tensile test, upper rolling grip. Let's replace the rolling grip, the lower rolling grip, by a confining pull-out box. And if we do that, it's small, but it turns out that we don't care about resistance. We care only on the onset of movement. And it turns out that the boundary effects are significantly minimized. All right, that's a device. And we run the tests. And this has, as of 3 months ago, there is an official test procedure developed by TxDOT that essentially quantifies this in order to define the suitability of a geosynthetic for stabilization applications. And guess what? We run the tests, and this is 1, 2, 3, 13 products, and measure the confined stiffness. Not all products are born the same. There is a difference, and the difference may be significant between product A and product B and product C. Now, this is not the end of the story, because this was run, this is not designed. So all these tests, and I didn't tell you that, were run against using a backfill that is a standard backfill. So essentially what this does is measures, it's like CBR. It measures the stiffness in relation to a standard backfill. So it's good for comparison purposes, not necessarily for design. But we need to tie this to performance. So let's go to the field. Let's go to the field. Oh, a new property, a single yet relevant parameter that quantifies the confined stiffness of the solid geosynthetic composite and the small displacement was defined. I love this saying. All models are wrong, but some are useful. All right, let's go to the field. I told you, TxDOT has been doing this for some time. So let's go to FM2. I told you, 32 test sections. Geosynthetic 1 and 2 and 3, reasonably similar confined stiffness. Remember that all of them did have similar performance. Here we go, control section, failed. And let's go to another section, SH21, near Austin, Texas. 3 types of geosynthetic. GeoGrid 1 worked, Geosynthetic 2 worked. Geosynthetic 3 worked. This is on the basis of the length of longitudinal cracks. Control failed. Okay, let's go to another one. FM 1644. Geosynthetic, a different geosynthetic, but with control section, and that's very, very important. Control sections, because all this is relative to the performance of the control. Control section did not work. Geosynthetic stabilized did work. In the vertical axis is the length of the percentage of longitudinal cracks. Another one, Cabeza Road. John is going to tell us a little bit more about this. Geosynthetic 7 worked. Geosynthetic 9 worked. No, they were not the same. Control failed. And here we have Geosynthetic 7, percentage of longitudinal cracks. Control, more longitudinal cracks. Geosynthetic 9, no longitudinal cracks. One more. This is the same one that I showed you in the very beginning. FM 1774, Geosynthetic 1, the one that had 3 different sections. FM 7, oh, no, I'm sorry. This is the one that failed. One that worked, 13. One that didn't work, 8. Maybe where this is a threshold that we're looking for. This is the one that I mentioned to you, that we had 3 sections, different thicknesses, control sections. These were the different sections in that case. Okay, geosynthetic thick base works. Geosynthetic control didn't work. Geosynthetic even with a reduced section did work. All right, and this is the final. So not only now we can establish what the property is and the magnitude of the property, but we did go to the field, and it was not easy. And we defined what is pass and what is fail. Even if you pass, not all geosynthetics are born the same. Some are going to be better than others. So according to Texot, and this was up to Texot, they define not only geosynthetic that passes, but geosynthetic type 1, type 2, and type 3. This is the very recent spec. So it's the previous spec, which I couldn't convince them to remove things that are useless. So the first thing that they did, they said, okay, let's add your property, but give me some time until we remove the others. So essentially what they did in here is they added the confined stiffness as a new requirement, and they added a type 3. They already had type 1 and 2. They added a type 3 to differentiate those that work well against those that work excellently well. This has been recently published. This is public domain. All the names and brands are not sanitized in the report, so you can get it. Okay, and what's new? Well, this is continuing. This is a project that is being constructed as we speak. I think that yesterday, I'm not sure, depending on the weather, yesterday was going to be the day. This is the first project that uses these specifications. So, US 82, that uses, is the first time that they are going to specify and use a type 3 geosynthetic. And more than that, believe it or not, Texas has never used base stabilization to reduce base thickness. Only is it state, probably either it's California or Texas, the ones that use the most geosynthetics in base stabilization. Texas never used it for base course reduction. Now they are changing that, because they got confidence on really understanding what is the property that matters. They're going to go in a big project, IH10. They are reducing the thickness from 13 inches to, from 13 inches to 11 inches because they add the geosynthetic, by the way, it's a type 3. This is that new project. It's going to be heavily being constructed. It's going to be heavily instrumented. And the objective in here is not to have to wait 10 years to see the differentiation between control sections and stabilized sections, but we're going to measure strains as an early warning of what the future performance may be. So, conclusions. The use of geosynthetics was found to effectively minimize the progress associated with expansive plays. It is clear that geosynthetics do work. They lead to a significantly smaller percentage of longitudinal cracks than control sections. Compared to lime treatment, by the way, we found this, it was not our objective of our study. Don't use lime treatment unless you go all the way through. The confined stiffness of the salt geosynthetic composite under small displacement was identified as a relevant property. An analytical framework and the experimental approach was developed to quantify it. And that property correlates very well with field performance. And with that, I thank you very much.